Well, thank you very much. What I'd like to do today is talk a little bit about the Sundram study because it is so unique. I'm sorry that Sundram can't be here. It's really his study, and I was part of the workup of the data once he got it. So we'll approach it from that perspective. By way of introduction, I'm at Brandeis University and have been there for about 25 years. And before that at Harvard in the School of Public Health Nutrition Department for 15 years. So I focus pretty much on fats and oils and atherogenesis, now more recently into diabetes and obesity, but still focused on the issue of fats and oils and now carbohydrate. And I think the study that we want to talk about here is related to that and of interest because it does raise some issues that we're trying to model again in animals to see if we can substantiate what we found here. I don't have to talk much about this because we've talked already about triglyceride structure, but just to remind you that there are 3 fatty acids on the glycerol backbone, and I like to think that the SN2 is very important, and as we'll discuss a little bit later, I think it's very important the way that you consume fat, and especially oils. You find that the 2 position is almost always unsaturated in natural oils and saturated in certain fats, specifically coconut oil, milk fat, and palm kernel oil. And they have very little 18.2. So they're saturated fats, and we think of them as bad news, and they are, but it's not just because they're saturated fats, it's because they don't have much SN2, 18.2, in my theory of things. So saturated fats per se are not bad, except for the fact they don't contain enough polyunsaturates. And we've done a lot of work showing that if you take a bad fat and you blend polyunsaturates with it, you can make it metabolize very normally, and you don't see the fitting of the curves and the observed and predicted observations that you would get from Ron's prediction equation. So I think there's a lot of room to negotiate here on how important polyunsaturated fats are and how specifically important are they to the SN2 position. And the SN2 position is almost always what you find in phospholipids. Most of them are 18.2 SN2, linoleic acid, and then omega-3s as well. So phospholipids are the workhorse here, I think. And you don't need much phospholipids, but you certainly need to have the proper amount. That's why we call them essential fatty acids, so you can make phospholipids. All your membranes in your body are composed of phospholipids. They have them in there as structure for lipid rafts and things. So, very key, and I like to think that there's something about the way we eat fats and the structure of having an SN2 or not as polys will have an impact on the phospholipids. That was why I was asking this morning about whether or not the gut, how much phospholipid does it make? If you're going to secrete a chylomicron, you need to have phospholipids. And if you don't feed enough, or if you've fed a saturated fat for a week or 2 weeks or a month or a year, are you depleting your body's supply of polyunsaturates? If you just do a postprandial meal, you have a lot of buffer in your system. You have the mucosal cells. You've got extra fatty acids in the gut. They come in to help out with the problem. And that's why I think it's very important. We'll talk later about how you go about this. The other point that I'd make is that ceramides and sphingolipids are very important structural lipids in rafts again. And now there's a very promising data set that shows that ceramides are involved in diabetes. They go up very high high levels in pre-diabetics and diabetes. So, and ceramides are dependent on having a required lecithin for their formation and so forth. So there's still a lot of molecular biology that one can look at here. And just to remind you about interesterification and how it works, again, focusing on this SN2 importance, when you start interesterifying with, for instance, canola oil and butter, and you put saturated fats into the mix, you play what I call fatty acid musical chairs, and when the music stops, everybody rushes for a sight, and you end up altering this natural formation, and you can put saturated fats in the 2 position, and the question is, if you interesterify fats, do they behave normally? And so we've done that study, accidentally almost in humans, but the end result was that we have a scenario that suggests that the results are leading to prediabetes. And I think that's a pretty serious accusation or concern if it's true. So it behooves us to try and get an answer to that. And so what I do here is I have a cartoon just to remind us that diabetes is really all about glucose metabolism. Elevated glucose, by definition, is diabetes. And what happens is you have 2 sources of glucose really in your system. One is from the diet. That's your main source. And it depends on what you eat and the glycemic load or the type of carbohydrate that you consume. So if you consume simple carbohydrate, you can absorb a lot of glucose readily and quickly. If you do complex carbohydrates and lots of fiber, you can delay the absorption of glucose, and that spares the glucose pool in the blood, and it spares the beta cell in the pancreas from putting out too much insulin too fast. And the glucose gets metabolized. One, it goes to the liver via the portal system, and the liver ordinarily clears the glucose and uses what it wants and puts it into storage as glycogen if it's at all low in storage. And it takes the excess glucose and either ships it out directly back out into the blood, or if it's really in excess, it starts converting it to fatty acids and triglycerides, and we get back into lipoproteins and lipoproteinemia and so on and so forth. And that's part of the metabolic syndrome. This, as Ron just pointed out, this gets large, these particles get numerous, and the HDL goes down, and particle numbers and size change, and so on and so forth. So glucose disposition by the liver is very important. And when glucose gets too high too long and the insulin comes out to play too long and too hard, it ends up producing insulin resistance in the liver, and at the same time it produces insulin resistance in the muscle and the adipose tissue. And so insulin resistance is simply saying, the tissues are simply saying, look already, I have enough glucose, I don't want any more, and it shuts down the transporters for glucose, and the glucose backs up in the blood, and what happens is the beta cell sees glucose rising in the blood, not from the gut so much now, but because the liver is pumping out this extra glucose and it's getting turned away by the depots, so now the insulin gets higher and higher and higher. And for an average of 10 years, you can fight the glucose load with high insulin. So if you have a history of diabetes in your family, or if you have developed additional weight since the time you graduated university, which most of us had, you should probably check your insulin at 40 or 50 years of age and find out if you're hyperinsulinemic, because that's a predictor that you're on your way to diabetes. So I give you this background because I think that's maybe part of the issue in the Malaysian study, in the study that we're talking about. So insulin resistance is very important. Glucose consumption, the amount that's in the test diet and the load and so on, and how long you consume the diet to sort of process your tissues and get them ready is important. So these are the data then that we had from the Sundram study, And I would point out over here that you can see the three different diets: palmolene, trans fatty acid by partial hydrogenation of soybean oil, as Ron pointed out, and interesterified with fully hydrogenated soybean oil, and then putting it back and interesterifying that musical chairs, if you will, with regular soybean oil. And there was quite a bit of this put back. Notice here that 18O represents, down here you can see it, 12% of the energy in that diet. That's a very high load. Now I must say that that load came from Peter Zock's paper. Actually, we modeled it after his. He had fed a study where he fed 18%, 12% energy from 18.0, and he compared it with 12% energy from trans, and used linoleic acid as the control, as I recall. And in that study, I would point out also that the interesterified fat data was identical to the trans data. There was no difference. So again, it doesn't quite fit with Ron's modeling, expected and observed. So the issue is, when you set up a model for predicting how the fatty acids are going, you have to pick certain papers and use them as your basis to make your model, and then you see if everybody fits it. And there are a lot of papers that don't always fit with the model, and sometimes they tell us something important, and sometimes they're out of whack, and we need to determine that. But having said that, you can see what happens over here to the total cholesterol response. It didn't differ in the total cholesterolemic response, but the LDL, 129 here versus 122, the LDL actually went up in the trans, and it was significant over the palmolene, as Ron pointed out. Interesterified, 18.0, had slight elevation in LDL, not significant really from palmolene, but you'll notice that both of these decrease the absolute value in HDL. So the LDL-HDL ratio, here it is 2.6 and 2.5, were elevated versus 2.2 in the palmolene. And we tend to use this. You could use TC over HDL. That's another risk factor, but LDL over HDL is a pretty good predictor of risk. So that was the reason for doing that. That was the design of the study. I wasn't really in on the design very much, but Sundram wanted to. He was making functional fats to make comparable fats that could be used interchangeably in making, in baking, and so forth, making different types of foodstuffs. That was the idea. So the plasticity of these was presumably about the same, and that was the background reading on it. Now, much to our surprise, when he ran the study and showed the lipoprotein results, we decided to look at the glucose levels. And this was done retrospectively, I have to add. I mean, the study was just finishing up and so forth, but so we hadn't put it in as the primary observation. But what he found in fasting glucose from 0 to 4 weeks on these diets, you can see that the palmolene raised the glucose level about 3%, which wasn't insignificant. Partially hydrogenated soybean oil raised about 9%, which was significant. And the interesterified raised 22%, which was highly significant. So he looked at the insulin, the terminal insulin values, and compared it with the initial, and you can see that, no, this is just the terminal for insulin, and the controls were 10.1 microunits per mil, 9.1 and 7.9, so minus 10% and minus 22%, which went right along with the glucose values, which was a little bit of a surprise. If you know diabetes again, you would expect type 2 diabetes developing, as I told you, your insulin levels tend to go up. So, how to explain that? Well, what he did was he ran a postprandial study, very similar to what Tom has discussed earlier, but he did a little bit differently because he ran his postprandial study 2 weeks into the feeding of the fats, not just getting people and say fast overnight and here's a meal. No, you eat my diet for a week or 2 weeks or some period of time to tend to acclimate the body to the fat that's being consumed, and then seeing what the fats do, feeding the same sort of meal that you'd feed the people anyway, and not a milkshake or something of that sort. So in the Malaysian study, the diets were prepared by a chef who's been doing this for years now, and it was sort of a metabolic unit where people would come in on campus and eat the meals twice a day. They'd have their main meal at noontime and then a snack in the afternoon, and then they'd get a lunchbox or fat to take home at night for any cooking they did there. But most of their calories were in the midday meal. And then the postprandial study was done, and you can see the results. Again, fasting in the morning, you'll notice already that the interesterified levels are slightly higher than either the partially hydrogenated oil, the trans, or the palmolene, and they continue to stay higher and then increased quite dramatically towards the end. Again, suggesting to me that there's something about the absorption, or maybe a delayed absorption, going back to what Tom said about having SN2 delay absorption, either from lard or interesterified palmolene. You delay absorption. One possible explanation is maybe the fat absorption was delayed by the IE, and so the carbs went ahead of the fats, and we're seeing a carb effect here, relatively speaking, more carbohydrate absorption in that period of time. I don't know. All I do is report the data. As David Krzyzewski said, data don't lie, only statisticians do. So we have the data, and I don't know all the answers. But if you look at the incremental area under the curve, again, you can see that interesterified was significantly bigger in terms of the glucose story. And it wasn't significant, but the trans was slightly less. Then, to back up the glucose data, we decided to look at insulin secretion in the postprandial period and C-peptide secretion. Again, as Tom pointed out, it's a good marker. C-peptide and insulin come out of the pancreas together in a product called proinsulin, and then it's cleaved, the peptide, the protein is C-peptide is cleaved off, and you have insulin. So it's a nice marker of what's being secreted, and you can see that palmolene was secreted more readily than the other two, and you can see down here that the C-peptide again was highest with palmolene and lowest with the interesterified fat. So it looks like the insulin levels have something to do with the secretion rate of insulin. Again, it's not necessarily what you would think if you're getting resistant to insulin and having a pre-diabetes situation. So let me just touch on a few points now in my last few minutes here. Based on that, and there are other papers in the literature that talk about insulin secretion. I'll put them in the final paper. I didn't want to dwell on all the slides here, but there's some that are showing basically no results there. And as Tom just pointed out in his study, his elegant study of lard and palmolene and so forth, they didn't see any insulin effect. I would remind you that's a postprandial study. There may be a major difference if you feed the fat for a while. So that's sort of the public health issue. If we're going to eat fats for a long time for the rest of our lives, we like to know that we're getting a long enough period of time to see a potential effect. But in general, the consensus is that fat per se is not diabetogenic. It can be in the sense that if you eat too much fat along with too much carbs and you don't exercise, you get overweight, and that's a high risk for diabetes. But if you correct for the overweight system and just look at people that eat a lot of fat and don't get overweight, they're not pre-diabetic, they're not going to diabetes. On the other hand, high carbohydrate, as I just showed you in my model earlier, high carbohydrate intake of simple carbohydrates is a relatively good predictor of risk for diabetes. Total fat, saturated fat, and monounsaturated intakes do not predict diabetes in normal, healthy women going forward. And all this comes from Salmeron and all, which is the Nurses' Health Study. And I always like to say that 80,000 women can't be wrong. So that shows that, again, you can't pinpoint saturated fatty acids per se as diabetic risk, and MUFAs don't seem to help much. But on the other hand, trans fatty acids are associated with risk. I think there's a lot of mechanistic data now to show why that might be. And my thinking is that maybe by looking at the trans fatty acid story long enough and hard enough and understanding how that works, we may get a model situation for understanding how high levels, remember 12% of energy from Interesterified 18.0 in the SN2, not all that 12% in SN2, but a large percent in SN2 can cause risk. And polyunsaturated fat can decrease risk about 20%. This is based on quintiles of intake. So I'm comparing the highest quintile with the lowest quintile. So the highest quintile intake of polyunsaturates in these nurses was associated with decreased risk. And that fits again with what I'm trying to model and tell you about, that if you get polys in the SN2 and make enough phospholipids, you're going to be okay. As I said, and I've done a lot of this in animal models, I can take butterfat, and if I blend it, butterfat's one of the worst, and coconut oil, if I blend it 50-50 with corn oil, you see no risk at all in terms of the lipoproteins. It disappears. So if you put enough, I think, phospholipid together from the foods that you eat and the fat that you eat, you can metabolize fat very well. So, concerning SN2 fatty acids, most natural fats, especially oils, contain only SN2, either PUFA or monounsaturated fatty acids, with the exceptions that I mentioned. And if you think about those exceptions, they raise cholesterol. Coconut oil, milk fat, and palm kernel oil. If I gave you that as your only fat, I can guarantee that everyone in this room would increase their cholesterol, and mostly in your LDL, but your HDL would go up too. And I thought long and hard about that, and I think there's a reason for it, especially breast milk, milk fats in all species. It's to raise your LDL. Why? Because when you're young and growing rapidly and still nursing, you have a lot of tissue formation, and your tissues can't make cholesterol fast enough. But if you have it in the liver or coming from the gut and transported right around, it can go under the cells when they're growing, and you can make membranes and stabilize membranes very quickly. You make hormones that you need and so forth. So there's a reason for it. But when you stop breastfeeding, your cholesterol goes down. Infants have pretty high cholesterols. We did a study with one of the Mead Johnson years ago, and we made different formulas, and if you compare the breast milk fed infants, their cholesterol is 160, but with the artificial formula and the fat changes, their cholesterol was 135, and it was highly significant. So, and that was with more poly. So you can see that changes the story. Sundram et al. Fed Interesterified 18.0 But if you listen to Tom today, I think that 16 SN2, 16-0, palmitate in the 2 position, would also have the same issues. And there's some lipoprotein data that is in my review earlier. Sheila Innes, who was mentioned today for infant formulas, she used piglets and infants to model this, and she showed when she fed beta pol to either one with a SN2 palmitic acid that the LDL went up and the cholesterol went up, mainly the LDL. So it also appears that SN2 fatty acids are difficult to metabolize. Again, I would interpret Tom's data with a slowed absorption. He mentioned that it was much slower in women, much slower than men, but and maybe gender is an important factor here to look for clues how this might work, but they're slow to metabolize starting with absorption. So they get to the small intestine, they don't absorb very quickly, or hydrolyze effectively, and maybe it's because they don't have enough 2-position 18-2 to make phospholipid in the gut to help move the fat out of the gut. If the gut mucosa cell starts filling up with fat, there are signals, including the enteric nervous system, sends a signal right back to the stomach and says, don't give me any more food, hold up, stop eating, and stop delivering the chyme into the small intestine. So that could be part of the issue here. One scenario for SN2 is metabolic dysfunction related to the glucose story that we talked about, relates to this atypical phospholipid or ceramide formation affecting membrane structure and function, and cell signals, because when you start metabolizing the diacylglycerol and prostaglandins and the other eicosanoids are very important for telling the cell what to do and keeping metabolism going. So there's still a possibility there, and I like to think that the Sundram story has just stumbled on something, in part because of the unusual level of 18-0 that was incorporated, and 2, possibly related to the genetic background. So come now to design issues for the future, something we should think about. Gender, I think Tom's data are very important, very critical to think about to help us design better studies. For now, if you really want to get at the issues, I would say stay with one gender so you can get a big enough N to have the statistical power you need, and probably start with males because they seem more susceptible to this type of manipulation than females, which seem to, as Tom put it, just blunt their effect from the get-go. Age is probably very critical. I know those of us have done some clinical studies, like to use university students, and because they're readily available and they like to do it, they're excited about it. But maybe they're not the best because they haven't put on the extra 10 pounds yet. They're not into a challenged metabolic system, and the body mass index is pretty lean. If you look at a lot of the studies, they're all 22, 23. The Malaysian studies were pretty lean people. But there's another factor here that affects the Malaysians. They have one of the highest incidence of type 2 diabetes in the world, in the native Malays. And there's a gene pool in South Asia that runs from southern India down into the Malay Peninsula that is well described, and I think I referenced it in the abstract. And they're different from the Chinese and the Indian population in Malaysia that's been described now. So maybe, and these are all Malays that Sundram studied, maybe they were just pre-diabetic to begin with, or had the genes, and we pushed the envelope too far. So diet design is important. The level of total fat, carbohydrate, and protein. is probably crucial. And I say that because I just pointed out in the earlier model, carbohydrate is the number one sinner, if you will, related to diabetes, type 2 diabetes, and fat actually can be protective if you provide enough polyunsaturates and don't put trans in there, and maybe if you don't put too much interesterified fat in there with saturated fat in the 2 position. Protein is important. There's a literature on protein in diabetes, the quality of protein and the amount of protein. Protein tends to be protective. When you do a postprandial study, very often the protein is not considered. You put in muffins and you put in fat, but you don't think about putting in the high quality protein or enough. Most of us in this room consume about 15 to 16, 17% energy from protein. A lot of the postprandial studies, including Sundram's, because we hadn't thought about it enough, was only 7% energy from protein. So what if you put too much fat and not enough protein? You can't make lipoproteins in the gut fast enough to ship it out, possibly. Percent calories from interesterified saturated fatty acids, just looking at the literature quickly, the Judd study shows that 8% energy you can see an effect in the lipoprotein. Below 8% energy from interesterified fat, you may not see an effect. Remember, we use 12% energy, as Peter Dock did. Metabolic status, use normal, healthy people, and you'll probably get a minimal effect. That's just reading through these 20, 30, 40 papers that I looked at related to either trans or interesterified and diabetes and not, and finding results or not results. Normal, healthy people are probably not who you want to study. Better off pre-diabetes or even type 2 diabetes. Here, there are papers that show fat effect on insulin secretion. Hyperlipidemia as well. All of them responsive? I don't know. But it's a bigger chance that you'll find something. And with the world growing more overweight as we speak, and type 2 diabetes as the number one disease in the next 25 or 50 years, I think it behooves us to think about this model. Find susceptible subjects and work backwards. What I mean is, it looks to me as though certain populations of people, maybe even the Pima Indians in the U.S., with a known thrift gene, and 80% of them have type 2 diabetes by the time they're 40 years old, because they were taken out of an ecologic niche where they didn't have any energy, any carbs, much to speak of, and the dry season was long and hot, as we know in Arizona now, and they had to get by with stored food, and they wouldn't eat, relatively speaking, for a few months. Then they eat again, and they quickly absorb or incorporate the energy and make a story out of it. So find a population that's susceptible, back off on the amount of trans. I mean, the interesterified, change it from 18.0 to 16.0, compare them and so forth. I don't know. Postprandial study for glucose or not, I've already mentioned. Fat differences may appear if the subjects are genetically prone. As we saw in the Malaysians, we did a postprandial study and it seemed to be there, but they were also pre-fed for 2 weeks before they were tested. Use type 2 diabetes or hyperlipid but not healthy subjects. Better to feed diet for 1 to 2 weeks or longer, and then do an oral glucose tolerance test. If you're really focused on glucose metabolism now, switch over from lipoproteins and start focusing more on glucose. Postprandial, probably not generally effective for predicting long-term results. Again, I want to know how the body is adapting to the fat we feed and or not, and then see the response after a few weeks and make the decision then. So it's best to preload the diet fat for at least several days. Single meal, Tom pointed out his people don't like to go hungry for more than the 3 or 4 hours, so you put another meal in, but that gives you another bump, and then you have the argument to, okay, here's why we did it, and the purists like to say, oh, let's just see what happens with one response, one meal, and so on and so forth. He mentions that he usually only uses one. Feed the same meal as diet composition in terms of the carbohydrate, fat, protein. And that's, again, a point. Do not feed more fat than carbohydrate in the test meal because fat can be protective and you lose the effect. So just looking at the Sanders recent paper, I calculated that this is carbohydrate, fat, and protein. Carbohydrate, fat, and protein. So the carbohydrate was quite a bit higher in the Sundram load, and the fat less. Protein the same, but here it was reversed slightly. So maybe that's part of the story. Make sure when you postprandial challenge that you do it right. So finally, just to summarize again, the model, the liver, muscle, adipose tissue, they have to handle the glucose load, and the glucose primarily is going to come from the gut, and the glycemic load is critical here, how fast you put it in and how quickly and with how much effort you put into making the beta cell respond will dictate how high the glucose goes. If the glucose goes too high and the insulin gets too high, you end up with insulin resistance in the liver and the muscle and adipose tissue, and overwork the secretion of the beta cell, and ultimately, after 10 or 12 years, when you finally go to the clinic and you say, oh my gosh, I don't feel well, it's because your beta cells are running out of insulin and you can no longer handle the situation. So, beta cell failure, reactive oxygen species, mitochondrial damage, so that there's a model that's nicely in place for understanding how possibly type 2 diabetes works, and I think it fits into our overall story. So in summary, SN2 fatty acids and glucose metabolism. Interesterified SN2 can affect glucose metabolism adversely. That's what the data said. Would seem to be expressed only in vulnerable subjects, so keep genetics and use people that have metabolic syndrome if you can. The level of SN2 saturated must be high, probably greater than 8% energy to observe an effect. Maybe not what's going to, after listening to what Dave said this morning, it's probably higher than we'll consume, but is the problem out there? Need to consider SN2 18.2 intake as well, because phospholipids are likely involved. Thank you very much, and be well, be strong, be kind.